So matter is anything that has mass and takes up space. Okay? And that's kind of like 8th grade science, even maybe like elementary school kind of like definition of stuff, right? And matter is everywhere. So like iron, made of matter. Spider, made of matter. Like literally everything is made of matter. Now, you're like, well, what is matter? What's like the basic kind of like thing that we count matter by or measure matter by, the basic unit of matter? And those are atoms, which is what we study in chemistry, right? We talked a lot about atoms. And whenever these atoms bond together, whether it's like an ionic, covalent, metallic, we learn the kind of bonds, we make molecules. Okay? So nothing, I think, too crazy on this slide. It's really just kind of a review, but you know, appreciate that like there isn't anything that exists that isn't made of matter, that isn't made of some of those elements that are on the periodic table. All right. Let's move on to the next slide. Now, we want to take matter and think of how can we organize matter to better understand things, right? Because otherwise, if we don't organize matter, it's hard to it's hard to understand like what properties might like certain kinds of matter have. And that's the idea of the periodic table, but like even like not just talking about just elements, there are other ways we can organize matter. And that's the two like general categories are a pure substance and a mixture. So I'll run through the difference between the two, but those are kind of the two, pure substance or mixtures, the two general ways that we can classify matter. So if we look within pure substances, so like focusing here, we can break a pure substance down into elements and compounds. So looking at elements, like the periodic table of elements, you have helium. You even have diatomic elements. So remember, oxygen is one of your diatomic elements. So O2, two atoms together. So even like, in other words, a lot of people, if I said like O2, some people will think that's a compound. It isn't a compound because a compound is two more different kinds of atoms, right? So water is a compound and oxygen isn't, because water is a molecule made of two different kinds of elements. Okay. Are we good here? Okay. So to back up, we went through pure substances, element, compound. So then a substance, whenever we're saying a pure substance, what we're saying is we can't, like what makes something an element is it's something that you can't break down by any other chemical reaction. Like any sort of chemical change, you can't break it down further. Now, y'all know Mr. Ecker, other chemistry teacher down the hall. Did you know? I don't know if did you know he has like a tattoo of the periodic table on his back? Yeah, just like a full back tat of a periodic table. Anyways, that's not him though. But it would be something kind of like that. You know, for obvious reasons, I can't just like get a picture of his back, you know, and put it on here. But yeah, you know, if you're, you know, I'm not like trying to promote or not promote tattoos or anything, but you know. If you're ever gonna get a tattoo, I suppose, like, you could go worse than the periodic table on your back. Anyways, yeah, so then we got more than 100 elements on the periodic table, and we can't break elements down. Element is something you can't break down any further by chemical means, by a chemical change. We good here? All right. So anyways, so talking a little bit more about compounds. It isn't like always guaranteed that you form a compound. You got to have the right conditions. Like in other words, like some elements don't want to form together to form a compound. Like certain elements will, like a metal and a non-metal. The nature of metals wanting to lose electrons and non-metals wanting to gaining electrons. That's why they're more likely to form a compound, like say sodium chloride, or like the ratio of like how many oxygen and how many hydrogens come together to make water. That's gonna depend on, you know, just like the different properties of like how many electrons each one needs. But anyways, point here is you get different elements together, you make a compound. All right, so talking about compounds, there's two characteristics of compounds I want you to know. The first is that whenever you combine like elements to form a compound, they always combine in the same proportion. So going back to like water, we say water is H2O. What that means is whenever hydrogen and oxygen come together, there's always two hydrogens for every one oxygen. And that proportion, anytime you're gonna combine oxygen and hydrogen, they're always gonna come together in that proportion. And the reason for that comes down to like the Bohr models and what each element would need to get that full valence shell of electrons. So in other words, it's a little harder for you to appreciate because we didn't make you draw Lewis structures in regular chemistry, but if honors, they would kind of understand maybe the slide a little bit better when they know like why do like certain elements form, the number of bonds they form, and stuff like that. Anybody know this reference? Waterboy? Adam Sandler? Anyways. Okay, now this slide is very interesting. So if you take whenever you make a compound like sodium chloride, you're taking the element sodium, the element chlorine, you combine them to make sodium chloride. But I think that the truly fascinating thing about chemistry, and it's fascinating, I don't care who you are, like you take this is sodium, this is what pure sodium looks like, right? This is what pure chlorine looks like. You ever heard of chlorine gas? Right? It can be like a biological weapon. You can take a biological weapon and you take like sodium metal, a block of metal, and if you combine them together, they make table salt that you put on your food and you eat. That's the wild thing with chemistry. In other words, it can be really it can be very difficult to predict the properties that a certain compound will have just from the individual elements that make it up. It's not like colors where it's like, oh, if I take red and I take blue and I mix them together, you get, what do you get when you mix red and blue? I don't even know. You get purple. And like that kind of makes some sense. You're like, yeah, I guess purple kind of looks like a mixture of red and blue. Like that's not completely wild, but you would never guess like that those two things would make that. So anyways, chemical and physical properties of a compound are going to be different from the elements that make it up. All right, so talking about a mixture, but let me back up and kind of orient you with where we're at. So we just finished talking about pure substances. Now I want to talk about mixture, so the other kind of classification of matter. So a mixture is when you combine two or more substances. Okay? So and this is key for a mixture, they are not chemically combined. A compound, you had different elements, but they were actually chemically bonded together with like the covalent, ionic, or metallic bonds we learned about a couple units ago. In a mixture, there's no actual chemical bond formed. There's no sharing of electrons. Maybe a good way of putting it. No sharing of electrons. Okay? We just mix them together. So for example, pizza. When you eat pizza, there's not like a chemical bond between this red onion and the cheese. That's not a thing. There's just the onion and the cheese are just like next to each other, Same with sand, actually. Sand is actually going to be considered a mixture because you could, if you were to be patient enough and have the right tools, you could separate out the individual like minerals that make up the sand. And probably a lot, if you've ever stared really closely at sand, you can see the different and there's different kinds of sands, right? That's why sand looks different on one beach versus another, right? Because the minerals and rocks and stuff that make up the one kind of sand is different from another sand, depending on its geological history. Same with blood. Blood, you can separate and isolate blood into different layers You don't need to know this, but like, you have like plasma. It's got a lot of like nutrients in it. You ever heard of people who give plasma? It's like a college students do that, a lot of nutrients are in plasma, but that's different than like the red blood cells. When we think of blood, we think of red blood cells. That's only about 45% of your blood. The rest, there's other things in your blood, like a small amount would be like immune cells that help you fight infections. Anyways, we call all those mixtures. This is key, each substance in a mixture retains its own physical and chemical properties. In other words, onions will still make you cry no matter if they're just laying next on a pizza. Like, onions don't just like stop being onions or have different onion properties just because they're on a pizza. Whereas if I go back here, clearly chlorine gas, chlorine when it's just by itself is different than whenever you have chlorine in a compound with sodium. There are different physical and chemical properties when they're combined together like that. Okay? All right. So looking some more at mixture, there are two different categories of mixtures. There is a homogeneous mixture and a heterogeneous mixture. So homo means same, hetero means different. So in a homogeneous mixture, different, the particles are uniformly distributed. So focus on just this picture here, like red, blue, red, blue, red, blue, red, blue. That's how you say colors, right? They're spaced out evenly. There's a consistent pattern. Heterogeneous is just like, there's no rhyme or reason for how they're spaced out. So steel, you zoom in on steel, all of the atoms that make up that steel are uniformly placed, spread throughout. Now steel is something that's known as an alloy. Because you might be saying, why is steel not a compound? Anybody know why? Why would steel not be a compound like NaCl would be a compound? Thank you. Edison. Why would steel not be a compound like table salt would be a compound? Anybody know? Notice how there's no steel on the periodic table. There's not an element called steel, so what is steel? Sure.
Should they not be chemically mixing two different elements?
Technically not, because to chemically mix two, like they're literally sharing electrons. So what is happening in steel? It's actually like a really big development in like the history of just like chemistry development that allowed us to like build skyscrapers and giant things. We could develop something as strong as steel. You know what's going on with steel? There's no steel element, so what is steel? It's clearly a metal. So if it's not a metal that's on the periodic table, what would that mean? It's a mixture of metals. Now, notice how I said mixture. It's not a compound because there's no actual, like, if you have, I actually don't know the two elements that make up steel. I'm curious. Somebody at their laptop open, Google, what elements make up steel? But the metals that make up steel, they're not literally chemically bonded because the two metals can't, like, physically share electrons to make a bond. They just have that C electron. What is it?
Iron and carbon.
Iron and carbon?
Yeah.
Oh, interesting. I don't know that. Iron and carbon. So iron and carbon, they're not literally forming a bond with one another. That's why we call it a mixture. Anyways, air. Air is a homogeneous mixture because the air in this room, the air right here and the air back there is the same, more or less. Maybe it's technically a little bit different here because like I'm just talking and breathing out all this carbon dioxide than over there, but like generally speaking, air is uniform. Same with rain, right? The rain that'd be falling, if it was raining out, the rain falling there versus the rain over there is going to be the same, more or less. Same with wine. Interesting example. Now, heterogeneous, ice and soda. Understand why that would be heterogeneous. This layer of the soda, where you have the ice cubes, is different from the bottom layer where the ice cubes didn't reach. Or soil. Depending on like archaeologists that will dig into the ground and take different soil, the soil will change at different levels, and that's going to reflect what the climate or civilization was like at that specific time. Okay, oil and vinegar. This is a heterogeneous mixture because oil will form a layer, and the vinegar, the watery layer, will form a different layer. Kind of like the Italian salad dressing. That's another heterogeneous mixture. Or cereal and milk. We okay with this? All right. So yeah, looking at some of the characteristics, like getting in a little bit more of like what makes a mixture different from like an element, a compound in terms of properties. Components in a mixture are not fixed. They can vary. In other words, if if you have a cup that has like sugar and salt, the percentage of sugar and salt in this cup can change, right? Maybe like just, depending on how much sugar you put in, how much salt you put in, that percentage can change. Same with like coffee, right? It can change. But when you make H2O, I told you that H2O, water, is always 2 hydrogens, 1 oxygen. It is fixed. The ratio of the proportion of how you combine the elements together to make water is always 2 H's, 1 O. No matter how many H2Os you combine together, you're not going to make a different proportion of those. Okay. All right, moving on. The second thing with the mixture is you can separate it by physical means. So really appreciate what I'm saying here. If I wanted to separate water, like I could take water and I could isolate it down. It'd be very difficult. I could isolate it down to where I just have 1 drop that is literally 1 H2O molecule. It would be impossibly small, but theoretically you could do that. But as soon as I want to break up this water into the hydrogen and oxygen that make it up, I can't do that by physical means. I would have to do a chemical reaction to break the bonds that hold that together. Mixtures are not that way. I can physically separate everything that makes up a mixture. So for example, sand and salt water. Sand has its own sand properties. Salt water maintains its own salt water properties. I can physically separate. I could filter out the sand by running it through like a coffee filter. I could then, and that would leave me with salt water, I could then by distillation. What's distillation? Anybody know? Sometimes you hear like a distillery, like getting into like whiskey or something, but actually, like, what's the principle behind that? If you're distilling something. North, good.
You have to like evaporate it and it goes.
Yeah, it's evaporation. You take advantage of the different boiling points of different substances. So here, I can boil the water, and because salt doesn't boil at the same temperature water does, the salt will be left behind, and then I can capture that water in like a different beaker or something. Okay, but we separated all of that by physical means. So some examples of physical separation would be filtration. Think coffee filters, distillation, boiling, magnetism. So like junkyards do this, right? Like you got like a scrapyard of a bunch of like metals and stuff. They can use a magnet to like isolate the metals from like the rubber or something that makes up the car. Chromatography. Anybody know what chromatography does? Or chromatography? That'll separate things by like particle size. It's kind of similar to filtration. Anyways, there's that. So moving on to number 3 here, looking at difference between like elements, compounds, and mixtures. Elements and compounds are always pure substances, and elements and compounds are always homogeneous. So that word homogeneous, that can apply to like when we're talking about elements and compounds. In other words, water is always, you have a bunch of H2Os, you have a beaker of water, that beaker of water will be homogeneous throughout. There's not like more water in the top part of a beaker and less water at the bottom. It's all water. It's all H2O. Okay? In other words, there's this thing as a heterogeneous substance. Or there's no such thing as a heterogeneous pure substance. Like to be a pure substance means you're homogeneous. You're the same throughout. All right. So here's a good summary slide of everything. So you have matter. If there is only one type of substance present, we call it a pure substance. Within a pure substance, if that pure substance is made of one type of atoms, we call it an element. If it's made of more than one type of atom, we call it a compound, like water. Now, if it's made of more than one type of substance, it's not a pure substance, then it's a mixture. If that mixture is the same throughout, like a cup of coffee, we call it a homogeneous mixture. If it is irregular, meaning it is not the same, irregular means not regular, not the same, we call it a heterogeneous mixture, like salad. Okay? Is there any questions on this? Haley, yeah.
Oh wait. With the way we tell if there's like only one, if the substance present, or if there's like more than one, that's like it was just like the example like
So like take air, for example, like if you were to break air down, air is made of like a bunch of different gases. You'd have like oxygen, you could have nitrogen, some hydrogen in there. So air would be a mixture because it's made of more than one type of substance. Oxygen being a substance, nitrogen being a substance. But they're not chemically combined. So the key is they can't be chemically combined. Here there's more like oxygen is different than hydrogen, but the reason why it's not a mixture is because there's an actual chemical bond here holding them together. Any other questions on this? All right, so if you look at your formative, I'll go ahead and pull it up here. The first part of it is just a matter classification worksheet. So just you working on classifying some matter. Now the second part, because to understand reactions, and this might be bad news to some of you, you have to understand naming. So I'm reviewing, I gave you some review problems on ionic and covalent naming. To understand reactions, and eventually we're going to predict chemical reactions. Like if I say, I give you this and this, predict what you're going to make. To understand that, you have to understand ionic and covalent naming. So in the slide deck, I gave you some review slides on naming stuff. Okay? So I'm going to leave this slide up here to help you review. Let me stop the recording.